Namaskar, my dear friends. Welcome to the lecture series of machine design. In this lecture, we are going to start our new unit, that is the unit number 5, internal combustion engine components. Okay, in which we are going to learn about the design of cylinder of internal combustion engine. Okay, now as you know that the principal parts of an engine are cylinder and cylinder liners, piston, piston rings and piston pin or cousin pin, then connecting rod with small and big end bearings, then crank, crankshaft and crank pin and valve gear mechanism. Okay, so the design of all these components or the principal parts, okay, we will learn in our later on videos. Okay, so now today let us start the design of IC engine cylinder. So cylinder and cylinder liner. So there are two basic functions of an IC engine cylinder. Okay, so the function of cylinder is to retain the working fluid and to guide the piston. Okay, so the cylinders are usually made of cast iron or cast steel. Okay, so since the cylinder has to withstand the high temperature due to the combustion of fuel, so therefore some arrangement must be provided to cool the cylinder. Okay, so the single cylinder engine such as scooters and motorcycles are generally air cooled and they are provided with fins around the cylinder. And the multi-cylinder engine such as a car are provided with water jacket around the cylinder to cool it. Okay. So the primary function is to retain the working fluid such as a mixture of air and petrol or air and diesel, while the secondary function is to guide the piston. Okay, so the combustion of fuel take place inside the cylinder and very high temperatures are encountered. So therefore, uh, two types of the cooling system, that is the air cooling and water coolings are provided. Okay, uh, the single cylinder engines are air cooled as we discussed. Okay, and they are provided with the fins over the outer surface of the cylinder, and excess heat of combustion is transmitted by the cylinder wall to the surrounding through the fins, and the fin that increase the surface area of the cylinder wall and improve the overall heat transfer coefficient. Okay, so here you can see the cylinder, okay, and the cylinder liners. Okay, so there are two types of the liners. Okay, you can see here, this is the water jacket and this part is known as the cylinder liner. So liners are of two types. One is the dry liner and another one is the wet liner. Okay, so this is the dry liner and this one is a wet liner. So the use of the separate cylinder liner has the different advantages. And what are the advantages of that? The cylinder liners are more economical because they can be easily replaced after being worn out. Okay, so it is not necessary to replace the complete assembly of cylinder, jacket and frame. Okay, and instead of using the better grade material for all parts of the cylinder assembly, only the cylinder liner is made of better grade wear resistance cast iron. So the frame and jacket can be made of ordinary cast iron. Okay, and the use of the cylinder liner, they allows for the longitudinal expansion. Okay, so a cylinder liner which does not have any direct contact with the engine cooling water is known as a dry liner. Okay, Here you can see this is the dry liner, in which it does not have any direct contact with the engine cooling water. Okay, and a liner which have its outer surface is in direct contact. Okay, outer surface is in direct contact with the engine cooling water. So it is known as a wet liner. Okay, so the cylinder liners are made of good quality close grain cast iron. Okay, that is the palladic cast iron, nickel cast iron, nickel chromium cast iron. Okay, so in some cases the nickel chromium cast steel with molybdenum may be used. Okay, so the inner surface of the liner, it should be properly heat treated in order to obtain a hard surface to reduce the wear. Okay, then materials. Okay, so as we discussed, the are gray cast iron with homogeneous and close grain structure. Okay, they are centrifugally cast. For heavy duty cylinders, nickel cast iron and nickel chromium cast iron are used. In some cases, cast steel and aluminum alloys are used for cylinders. Okay, uh, the desirable properties of materials for cylinder and cylinder liners are: it should be strong enough to withstand high gas pressure during the combustion of fuel. Okay, it should be strong enough to withstand the thermal stresses due to heat transfer through the cylinder wall. Okay, and it should be hard enough to resist the wear due to piston movement, and it should have good surface finish to reduce the friction and wear during the piston movement, and it should be corrosion resistance. So these are the desirable properties of material of cylinder and cylinder liners. Okay, now let us discuss about the different design of the different parts of the cylinder. So first one is a bore and length of cylinder. Okay, bore means the diameter of cylinder and length of cylinder. So in engine terminology, bore means the inner diameter of cylinder. Okay, so the main dimensions of the cylinder are calculated by using the equations, okay, from the applied thermodynamics. So you know that the IP is the integrated power. Indicated power is equal to BP, that is the brake power upon eta. Eta is the efficiency. Okay, equation number 1. So IP is indicated power or power produced inside the cylinder in watt. Okay, and BP is the brake power or power developed at the crankshaft in watt. Okay, eta is the mechanical efficiency in a fraction. Okay, so in example where the mechanical efficiency is not specified, so it is assumed as 80% or 0.8. Okay, so here N is equal to capital N for two-stroke engine, and N is equal to N by 2 for a four-stroke engine. Okay, so N is equal to N for two-stroke engine, and N is equal to capital N by 2 for four-stroke engine. Okay. So where small n is the number of working stroke per minute. Okay, number of working stroke per minute, and capital N is the engine speed in RPM, revolution per minute. Okay. Then here you know that the indicated power IP is equal to PM LAN by 60. Okay, this equation indicated power is equal to, we can say in short, plan by 60, that is the PM LAN, where PM is indicated mean effective pressure, okay, in Newton per mm square or megapascal. L is the length of stroke in meter in the cylinder, and A is the cross sectional area of the cylinder in mm square. So we know that if the D, capital D is the diameter, bore diameter, then we can say area A is equal to pi by 4 D square. Okay, cross-sectional area of the cylinder is given by pi by 4 D square. Okay, N is the number of working stroke per minute and D is the diameter of cylinder or bore diameter, we can see in millimeter. Now, here the L by D ratio, okay, stroke to diameter ratio for the cylinder is assumed from 1.25 to 2. Okay, so in example, where this L by D ratio is not specified, then it is assumed as a 1.5. Okay, so therefore, here we can say L, okay, stroke length is equal to 1.5 D in millimeter. So therefore, in meter, it is 1.5 D by 1000. Okay, so stroke length, you can find the stroke length from this equation 1.5 D by 1000 in meter. Now let us find the thickness of a cylindrical wall, right? So if the cylinder wall is subjected to the gas pressure and the piston side thrust, okay? So the gas pressure produce two types of the stresses. One is the longitudinal stress and second one is the circumferential stress. Okay, so these two stresses act as right angle to each other. So therefore, the net stress in each direction is reduced. Okay, so for that, the engine cylinder or the cylinder liner is treated as a thin cylinder. So for that, the equation T is equal to P maximum into D upon 2 sigma C plus capital C. Okay, PD by 2 sigma C, because the cylinder equation for the thin cylinder, as you have studied in subject design of muscle element and the design of pressure vessel. Okay, so where this T is the thickness of cylinder wall in millimeter, P maximum is the maximum gas pressure inside the cylinder, Newton per mm square or megapascal. Then D is the inner diameter of cylinder or cylinder bore. Sigma C is the permissible circumferential hoop stress for cylinder material. Okay, permissible circumferential, or you can say hoop stress. And this C is known as a reboring allowances in millimeter. Okay, reboring allowance. So in example, where the maximum gas pressure inside the cylinder is not specified, okay, so it is assumed as 10 times of the indicated mean effective pressure. So therefore the P maximum is taken as 10 into PM. PM is the mean effective pressure, indicated mean effective pressure. Okay, and this circumferential hoop stress sigma C is the allowable tensile stress sigma T. Okay, so since the cylinder material is brittle, so therefore we can say sigma C into sigma T is equal to SUT upon factor of safety, where this SUT is the ultimate stress of the material. Okay, so this hoop stress is given by SUT upon factor of safety. In example where the ultimate tensile strength of the cylinder material and factor of safety are not specified, so the allowable circumferential stress sigma C is generally taken as 35 to 100 Newton per mm square. Okay, and the reboring allowance is taken from table. Okay, so reboring is required to compensate the uneven wear on the inner wall of the cylinder. So reboring allowance is the additional metal thickness over and above that required to withstand the maximum gas pressure inside the cylinder. Okay, so this it is provided to compensate for reboring at intervals during the lifetime of the cylinder. So you can see the reboring allows for IC engine cylinders. They are given here. It depends upon the diameter. Okay, so if the diameter is 75, then C is 1.5, then 100, then 2.4, 150, then 4, 200 is diameter, then 6.3. Okay, so up to the 500, if the maximum diameter is 500, then value of the reboring allowance is taken as 12.5 millimeter. Okay, so by this way you can select the value of reboring allowance C. Okay, now there are some empirical relations. Okay, empirical relations for the cylinder. So the thickness of wall, which varies from 5 to 25 with depending upon the cylinder bore. So it can be calculated by using the empirical equation, that is T is equal to 0.045 D plus 1.6 millimeter. Okay. Then the thickness of dry liner is taken as 0.03 D to 0.035 D, where D is a bore diameter. Okay, so all these dimensions are in terms of bore diameter or with reference to the bore diameter. Then thickness of water jacket wall is taken as 1/3 T to 3/4 T. That is the 1/3 thickness to the 3/4 T. Then thickness of the water jacket wall in terms of the diameter. It is taken as 0.32 D plus 1.6. Then water space between outer cylinder wall and inner jacket wall. Okay, water space between outer cylinder wall and inner jacket wall is equal to 9 mm for 75 mm cylinder bore to 75 mm for 750 mm cylinder bore. So the value is in between 9 to 75 mm for the diameter of between 75 mm to 750 mm. Then water space between outer cylinder wall and inner jacket wall in terms of diameter, it is 0.08 D plus 6.5 millimeter, and thickness of cylinder flange is equal to 1.2 T to 1.4 T. Okay, so thickness of cylinder flange 1.25 D to 1.5 D, where small d is the nominal diameter of bolt or stud. Okay, and radial distance between outer diameter of flange and pitch circle diameter of stud is equal to D plus 6 to 1.5 D millimeter, where D is the nominal diameter of bolt. So these are the different empirical relations. That means empirical means the relation which were developed by the past experience. Okay, they are used for the design of cylinder. Now, stresses in cylinder wall. Okay, so you can see there are cylinder. Okay, here the inside pressure is P maximum. Okay, and diameter is D. Here sigma C is the hoop stress. Okay, circumferential stress, and here you can see this is the longitudinal stress sigma L. Outer diameter is DO, P maximum, and inner diameter is D. Bore diameter is D. Right. So here from the equilibrium, okay, from the equilibrium, we can say this dP maximum, okay, equilibrium of the stresses, you can say dP maximum, okay, D into P maximum is equal to 2 sigma C into T, because this thickness is T, okay, and the stress sigma C downward in downward direction and here in both sides. So therefore it is 2 sigma C into thickness is T. So therefore dP maximum is equal to 2 sigma C T. Okay, force is acting on upward direction is equal to forces acting on downward direction for the equilibrium. So from that, we can say sigma C is equal to P maximum D upon 2T. Okay, so circumferential stress is given by P maximum D upon 2T. Now, from this figure, okay, we can say the P maximum into pi by 4 D square. Okay, force is acting on upward direction is equal to sigma L longitudinal stress into pi by 4 dO square minus D square. Okay, so from that we can say the longitudinal stress sigma L is equal to P maximum into D square upon dO square minus D square. Okay, so you can find the circumferential stress and longitudinal stress from these two equations. Now net stress. So the two principal stresses, the circumferential and longitudinal stress, are tensile stresses and they act at right angle to each other. So therefore, okay, so net stress in this direction are reduced, and net stress are given by sigma C net is equal to sigma C minus mu sigma L, and sigma L net, okay, longitudinal stress net is equal to sigma L minus mu sigma C. Okay, where sigma C is the apparent circumferential stress, sigma L is the apparent longitudinal stress, net circumferential stress, net longitudinal stress, and mu is the Poisson's ratio. So the cylinder material is usually brittle, such as cast iron. So the value of the Poisson's ratio is taken as 0.25. Okay, so two types of the stresses in cylinder wall. Now let us design of the cylinder head. Okay, so in most of the IC engine, a separate cylinder head or cylinder cover is provided. So the cylinder cover which accommodate the inlet and exit valve, air and gas ports, and spark plug in case of petrol engine, and atomizer in case of diesel engine. Okay, so the three parts are accommodated by the cylinder head. So in the preliminary stage of the design, the cylinder head is assumed as a flat circular plate, and its thickness is calculated by the equation TH. Okay, so TH is equal to D root Kp maximum upon sigma C. Okay, where TH is the thickness of cylinder head, K is a constant, and the value of K is equal to 0.162 generally is taken as, and sigma C is a allowable circumferential stress, and D is a bore diameter. Then design of stud for cylinder head. Okay, so stud are used to make the assembly of cylinder head and gasket, and which provide a leak-proof joint, right? So number of studs. Okay, so the number of studs Z, it should be between the units. Okay, so minimum number of studs is given as 0.01 D plus 4, and maximum number of studs is equal to 0.02 D plus 4 into 25.10. Okay, so diameter of stud. The core diameter of stud is obtained by equating the maximum gas force acting on the cylinder cover to the resisting force offered by all stud. Okay, the core diameter of stud is obtained by equating the maximum gas force acting on the cylinder cover to the resisting force offered by all stud. So that gas force acting on cylinder cover is equal to pi by 4 D square, that is the area, into P maximum. P maximum is the internal pressure, that is the gas force acting on the cylinder cover, and resisting force offered by all stud, that is the Z is the number of stud, pi by 4 DC square. Okay, area of the stud into sigma T. So equating equation A and B, so you will get the pi by 4 d square P maximum is equal to Z pi by 4 dc square into sigma T. Okay, where dc is the core or the minor diameter of stud, Z is number of studs, and sigma T is the allowable tensile stress for stud material in Newton per millimeter square. Okay, so the nominal or the measure diameter, okay, they are taken as usual as discussed in earlier slide. So studs are made of steel, and since the material is ductile, so sigma T is equal to SYT upon factor of safety, where SYT is the yield stress. Okay, and in example where the yield strength of the stud material and factor of safety are not specified, then the allowable tensile stress is taken as 35 to 70 Newton per millimeter square, and the nominal diameter of stud is obtained by the relation D is equal to DC by 0.8. Okay, D is equal to DC by 0.8. Then pitch of the stud, the pitch circle diameter of the stud is obtained by the empirical relation, that is dP is equal to D plus 3D. Okay, so therefore pitch of stud is equal to pi dP by Z, where Z is the number of stud. Okay, so minimum pitch is equal to 19 root D and maximum pitch is equal to 28.5 root D. Okay, so from these empirical relations, you can find the pitch of the stud. Okay. So I hope you can understand very well about the design procedure of the cylinder, okay, and cylinder head and different parts of the cylinder. Okay, so in our next lecture, we will solve the different examples of the cylinder. So thank you very much. Thank you, friends.